Hi there and welcome to this segment on volcanoes. In this lecture we're going to spend time talking about volcano types. You should have already listened to the lecture on eruptive styles, and you're going to see that there's a very clear connection between how the lava comes out of the ground and the kind of construct it'll make as a result of that. So let's go ahead and get started. Let's go ahead and go to the next slide. So I showed you a similar diagram to this in the last segment, silica content and explosivity. And basically we spent time in the last segment talking about these eruptive styles. And we're going to now talk about the different constructs that can come from these kind of eruptive styles that we have down here. I want to start off with what are called stratovolcanoes, which actually it shows up here as a medium explosivity, but basically only in the medium category because what we've ranked as high has a lot to do with this rhyolite caldera complex, or what is also could be known as a supervolcano. That would definitely relatively be much higher than a stratovolcano. But when you talk about the type of volcanic eruptions that we've had in historic time, stratovolcanoes can produce some of the largest types of eruptions that we've seen and fall into the Plinian or Volcanian category. So let's go ahead and take a look at some of the details for stratovolcanoes. Now, stratovolcanoes can actually produce eruptions that come out mafic, intermediate, and felsic. So all the types of eruptions can come out of this particular vent. Now, it depends on what part of the life cycle of this volcano you're looking at too, as to what kind of volcanic eruptions you might see. If you're looking at its very early history, so right when the volcano first started to be, it actually would have looked a lot like a stratovolcano at first, because basically what comes out of these vents are going to be more mafic. And this is because of the fact that when you first get a magmatic source to begin with, a lot of the hot, more mafic composition magma is going to want to come out first because it's more hot and more buoyant, less viscous. It's going to have the easiest time to escape. So out of that magma chamber, that type of material is going to come out first and usually make up the base of the volcano. If you take a look at the shape, you'll notice how, if you look at my cursor, how it's very broad at really low elevations. Part of that has to do with the tephra that comes out of the volcano. Tephra is basically chunks of pyroclastic kind of material that come out of the vent, broken up rock and ash and things like that. Some of that shape's coming from that, but you'll notice if you hike up a stratovolcano, not only do you see that, you'll see a lot of your mafic flows very close to the base of the volcano. If mafic lava does happen to erupt out of the top of the vent in its later life, more mature stage of the volcano, it's going to be very fluid anyway and not want to really hang out up here. It's going to flow very easily and freely down to the base anyway. So mafic eruptions are possible out of a stratovolcano. You'll not really see them associated or categorized that way in a lot of especially popular literature. You'll see them more associated with the intermediate and felsic variety materials. And as you walk up the volcano, you certainly have intermediate and felsic rocks. If you're walking up this, not only do you see the tephra and the ash deposits, you also see, as it steepens up, a more viscous magma that turns into rock, and when it turns into rock, it'll steepen up the volcano at the very top as a result. These kind of volcanoes, they'll blow their top off regularly, and in fact, this is Mount St. Helens before it had its eruption in 1980. And now that whole top of this volcano is gone. After that eruption, it blew off its top, but is actively building its cone back again. And in the last segment, I actually showed you some of those flows that were starting that process off. It wouldn't happen within our lifetime. It's a very long process by human standards, but by geologic standards, it's actually a blink in time as far as rebuilding its cone is concerned. All right, so let's go ahead now and go to the next slide. And I want to talk about shield volcanoes now. In contrast to the stratovolcano, which is basically made up of all different compositions that we've talked about except for ultramafic. So the composite cone slash stratovolcano is made out of mafic, intermediate, and felsic rocks. Shield volcanoes are strictly mafic. There is no variation in the composition. I'll repeat that one more time. Shield volcanoes are all mafic. There's no intermediate, there's no felsic. About the best you might see in variation, you might see little pieces of ultramafic inclusions in the mafic basalts. That's about the extent of the variety. So because it's all mafic and it's made out of entirely very hot lava, the volcano is going to not only be very large, because this lava has no problem erupting to the surface because of its low viscosity and high buoyancy. It also spreads out very thin and in all directions. And so the volcano shape that you see here, not very steep, you see that's basically flat, but it's also very large. This is the largest kind of volcano you can get. And let's take a look at the next slide. Actually, I'm going to skip a slide here. We'll come back to cinder cones in a moment. But I want to go right to this image. This is an image of Mauna Loa, and if you Google images or if you've been there yourself, you probably have your own photos of Hawaii, and this is a photo of Mauna Loa. What I mean by very large is this volcano has built up from the sea floor to the peak of this volcano is 56,000 feet above the seafloor. That is a lot of lava. Just to give you reference, Mount Everest is 29,029 feet tall from sea level to the top. You measure Mauna Loa from sea level, so the surface of the ocean, to the top, it's about, I think it's about 15,000 feet or so, it might be 12,000 feet. But from the seafloor, it's 56,000 feet. So that's tremendous. That's definitely the biggest mountain from base to top that there is on the planet. And it's basically because it's made up of all mafic flows. So let's go back to the shield volcano slide here. And so as far as size is concerned, you know, this might look pretty mild on the cartoon diagram, but we're talking about a huge structure compared to any other structure we're going to talk about today. All right, so the shield volcanoes are usually made up from what are called hotspot volcanism, and we'll talk about hotspot volcanism in just a few minutes. Let's go ahead now and talk about the third most common type of volcanic construct, and that is cinder cones. These are also all mafic, and they're steep-sided, but they're not steep-sided because they're made of viscous flows, because obviously they're not being all mafic. In other words, there's no intermediate composition magma, there's no felsic magma with this, it's all mafic. So it's made out of very fluid material, but what happens is it's made out of a pile of cinders, not out of the flows that we have with the other two types of volcanoes. So the cinders just kind of pile up. We talked about strombolian eruptions in the last segment where we had magma spraying up, solidifying in midair, and then landing. And its landing is basically these pieces of rock that you see now left behind here. So they can basically pile up to 500 to 1,000 feet tall. They are generally short-lived events. They could last a couple of days, or they may last a couple of years. And obviously, the taller they get, the longer the event has lasted. I'd say if it gets up to towards 1,000 feet, the eruption sequence was probably 2 or 3 years long tops. They don't really last much longer than that. And this kind of volcanic construct can be found in many different volcanic environments, including subduction zones. hotspot volcanism, I'll talk about that in just a few minutes. Um, just about anywhere you can get magma coming up, cinder cones may be a part of that sequence. It's pretty liberal. And this is again because mafic lava has an easy time coming up to the surface, whether it be in a small quantity to make up a cinder cone or in large quantities to make up a shield volcano. Because cinder cones, as I mentioned, only can last up to a few days to 3 years tops, once that eruption is done, it's done, meaning it doesn't re-erupt again several years later. So cinder cones, once they finish their eruptive sequence, are then therefore called extinct. They do not re-erupt again. So, and we've never seen, there's literally thousands upon thousands of cinder cones around the world, and none of them have re-erupted again since their first eruption. Other cinder cones have popped up in nearby locations, but the actual cinder cone that's already been created doesn't start up again. So these by definition become extinct once they are done. All right, so let's go ahead now and talk about hotspots. I'm going to talk about hotspots that are oceanic first, and these are probably the most mild type of volcanism. We're also going to talk about continental hotspots as well, and this is where we get into what are called supervolcanoes, where they come from. But hotspots are basically plumes of very hot rock that come from the mantle core boundary. There's basically known areas at the core mantle boundary that are much hotter than other places around that boundary. And because it's hotter, it's also more buoyant, so this rock will slowly rise up to the surface. Now, at some point, it's going to reach a point where it can melt. And there's a lot of debate as to how high that rock has to get up to actually melt by decompression. But there's been some recent research that was published in January of this year that has suggested that perhaps that magma can be liquid deeper than what we previously thought. We thought that perhaps the magma we couldn't have magma existing in the Earth's interior deeper than 70 kilometers, which is well within the lithosphere of the planet. But recently we have found that water and carbon dioxide actually exist much deeper than previously thought. We thought that the water and carbon dioxide were mostly brought in through subduction. And that's still true, mostly it is, but we've also found that there's remnant water and carbon dioxide much deeper down. And so we are actually finding that perhaps we might have little magma pockets as deep as 200 kilometers, which is still just underneath the lithosphere. So we have the lithosphere being 100 kilometers thick, and we're just saying, okay, another 100 kilometers down, we could still have liquid at that point. And then once you get deeper than that, it's actually solid rock. The pressure is just way too great, even with the water and carbon dioxide down there. So that's actually cutting edge research that's just being published right now on this subject. And I'm not saying don't interpret it as now the asthenosphere is liquid, because it's not. We're talking about little tiny pockets in comparison to a big layer. So it's just a kind of interesting. It's mostly fascinating for volcanology, so we can understand better how and where magma is coming from. So anyway, we have these plumes coming up, and as you know, plates move. Plates are moving across the planet. We learned that in the plate tectonics module. But the plume coming from the asthenosphere and coming from the core mantle boundary, actually, that coming straight up to the surface, is stationary. It's not part of a plate, but the plate's moving above it. And so what you get because of that is the magma coming up and creating a brand new volcano. So you have this eruptive center, the magma comes up and creates that volcano, right? Because this plate is moving, it takes that volcano and moves it out of the way. And so now pretend that, the volcano we just talked about is now right here. And then another volcano is created, and over time that plume is feeding that system. But the plate moves it out of the way as well. So basically what you end up getting is a chain of volcanoes that are progressively older as you move away from the mantle plume. That's what Hawaii represents, amazingly. And let's take a look at this in kind of a map view here. So this is a map of just the part of the chain that's actually above water, so the actual islands themselves. There's actually the main island of Hawaii. That's where the plume sits right now. It's actually sitting mostly right here. And the main island of Hawaii obviously has been created. These numbers are basically millions of years. So 0.43 million years or 430,000 years ago, that part of the island was being created. You could see right now a lot of the islands being created right here. And Loihi is actually underwater, but it's actually actively erupting lava as well. And not in our lifetime, but thousands of years into the future, that's actually going to pop up as an island at some point. But the plate is moving in that direction, so following my cursor. Started Hawaii, the plate's moving like that. So the oldest islands are Kauai here. Now, the chain did not start at Kauai, because if you look out further, here's the islands of Hawaii right here, and then you go out where there's no islands. We call those seamounts. They're away from the plume, and you can see that they get much older. Look at these numbers. And they actually end up going all the way to what is known as the Aleutian Trench. And we all know what trenches are, right? They're where subduction, it's a subduction zone boundary. So basically these seamounts have basically gone all the way, pushed all the way to the Aleutian Trench. This means we do not know how old this hot spot is, because its oldest traces have been subducted in the Aleutian Trench. But we can see that at least with some of the oldest seamounts, here's one that's 60 million years old, we know at least it's that old. But we can't know how much older it is because all evidence has been moved. Now, another interesting little fact before we move on to the supervolcanoes, and you're going to find this really interesting, is notice that there's a bend in this sequence. So based on what I just told you, we know the plate is moving in this direction currently, but at some point it was actually moving more north-south, moving towards the north basically. And at some point it changed its direction to a more northwest direction. And that history actually ties into our own history here in California with the San Andreas Fault. Look at the timing of this bend. It's at about basically 50 million years old. Our San Andreas Fault is also around 50 million years old. It's not much older than that. Before the San Andreas Fault, we had what was called a subduction zone, where we had basically what was called the Farallon plate subducting underneath the North American plate, right where we're at. And there's a lot of evidence to subduction that is in California today. The Sierras actually represented the volcanic arc for that subduction zone. The volcanoes are long gone. They've long since eroded away. And what's exposed there now are granites, and those are the old magma chambers that have since solidified and been pushed up to the surface. So these magma chambers are extremely old granites, several tens of millions of years old, to over 100,000 years or 100 million years old in some spots. Sequence. So we've got evidence that subduction used to happen here. Not today. We have the San Andreas Fault plate, transformed plate boundary here today. But what does that have to do with this bend? Well, the plate must have rotated. And that's kind of hard to imagine. How can a big old plate, the Pacific plate, completely rotate itself from this northwards direction to this more west direction? And what happened is, remember when we talk about subduction, there's one plate diving underneath another one. Well, what's pushing that plate to go underneath another plate? Well, somewhere there had to be divergence, allowing oceanic lithosphere to be pushed toward our coastline. And so what happened is that mid-ocean ridge needed to be subducted so that we no longer had subduction anymore, because the mid-ocean ridge would be gone and we no longer have oceanic crust being pushed toward us any longer. Well, that mid-ocean ridge got stuck in the subduction zone. Yeah, it got stuck. And it didn't like to go in parallel to the subduction zone boundary. It was basically lodged at that point. And the plate had to basically rotate itself to a more northwest direction to accommodate that mid-ocean ridge getting subducted underneath us. And that's exactly what happened. It was just too tough for the plate to actually push it down there on its own, so the plate rotated, and then the ridge got subducted. And then from then, where the plates met, where the Pacific plate meets the North American plate in California, that motion was now accommodating transform motion, because the Pacific plate's now moving northwest. And that actually allowed for the transform motion we see here today. An incredible history, and if you didn't quite follow everything I said, re-listen to it, because there were a lot of details that I think if you hear it again, you'll be like, oh, I kind of see what she's talking about. It's just an incredible tie-in, and it has to be the case. Now, of course, today we have transform motion. Will we have subduction on our coast again? Actually, it's unlikely right now. In the geologic future, it's showing completely just transform motion for a long ways out. So our subduction history is long gone. However, the Pacific Northwest still has subduction, northernmost California, Oregon, and Washington. And as the subduction, as that plate continues to subduct, eventually the San Andreas Fault will move northward, and the whole U.S. west coastline will have San Andreas Fault as its boundary in several million years from now. It's a long time geologically, or human life speaking, but geologically speaking, again, just a blink in time. All right, so let's go ahead now and go to the next slide. And I wanted to show you all the hot spots around the planet. You'll see the explanation there for what all the symbols mean. But I just really wanted to show you where most of the major hot spots on our planet are, where these mantle plumes are coming up to the surface. Most of them, a great majority of them, are coming up at the ocean, in the center of oceanic plates. Few of them sit at plate boundaries. There's no real rhyme or reason where they need to be, but most of them are in the ocean. And that would make sense, because our oceans make up 70% of our surface of our Earth. So there would be more likelihood of them being under our oceans. However, there are some on the continents, and when they are under the continents, they're actually going to behave a little bit different than they do in the oceans. In fact, I shouldn't say a little bit. It's quite a bit different than our oceanic hotspot system. So let's go ahead and take a look at the next slide and take a focused look in at Yellowstone in particular. So our Yellowstone volcanism is actually called a rhyolite caldera complex. It is a big, huge volcano that is so big, when it erupts, it actually evacuates a big, large area, and there's a lot of sinkage that goes on. So it's not going to actually protrude above the surface. After an eruption such as this, it's actually a big indentation in the surface. And that's why we call it a caldera. It's just a very massive, big opening, and that's what calderas actually represent. Usually, I think the measurement for a caldera has got to be greater than a mile wide, but for Yellowstone, we're talking about many, many, many miles wide. It's a very large caldera. But what I also want to focus your attention on is the sequence of volcanism that's underneath it. You'll notice here's our brittle zone, and here's our ductile zone. So this is our lithosphere, and this is our asthenosphere. And it's a very complex type of thing going on here. This is 40 kilometers depth here. And basically, it's basically very thinned out lithosphere, first of all. Usually our lithosphere on average is about 100 kilometers thick, but we've got some separation going on, pulling apart, that is thinning the lithosphere in this zone. And because this is being thinned so much, because these rocks are being pulled apart, this magma preferentially will want to come up in this zone. And it starts off mafic. It's rising basaltic composition magma, and we get some zones where we get the magma getting converted, because what's going on is it's starting to enter an area that is heavily continental in composition, so we know that's highly felsic. And so this mafic, through a lot of different process that we've talked about in the previous segment of this lecture, through like squeezing through openings and things like that, separating out mafic from felsic, we end up getting a very silicic or felsic magma reservoir right underneath where the caldera sits. And a lot of times we'll see what's called a resurgent dome inside the caldera. You'll see that's a little bit higher than everything else, and that's being pushed up from the new magma that's coming up to the surface. Once the pressure starts to build up strong enough from all this magma coming up and the gases and things that are associated with this, and that pressure super exceeds the rock strength in the caldera, we'll have another massive eruption again. These eruptions are not common. The pressure takes a long time to build up because these rocks are incredibly strong. And so it takes a lot of time, a lot of pressure build up to get this to erupt. And so the recurrence interval tends to be about every 700,000 years or so for the Yellowstone caldera. So as you can see, it takes a long time. And we're not within that zone of recurrence. Although, you know, it's an average, that recurrence interval is. So obviously it could happen earlier or it could happen later. And geologists give this a very low chance of this happening in our lifetime. So we're probably pretty safe from this kind of eruption. At least, you know, maybe our future generations may not be, but we probably are. However, we constantly monitor this volcano. We monitor its earthquakes, we monitor where the magma is, and we also pay close attention to where smaller eruptions might happen. Because even though a massive eruption is not probably likely, smaller eruptions could happen. And of course, if you're in Yellowstone and that happens, you don't know where that might actually take place at. So we keep a very, very close eye on all of that there. As part of this module, I should have posted a video, if it's still available, sometimes it is, sometimes it isn't, on supervolcanoes. And it's done by National Geographic. And so this will give you a lot more details to that I'm not going to give in the lecture. The last slide here is just like the Hawaiian Islands have a chain of volcanoes related to hotspot and plate motion. I wanted you to see that indeed Yellowstone's hotspot, it also has a chain. It's not an island chain because it's on the continent, but it's a series of volcanic signatures that we can see is related to plate motion. So right now, that's where the hotspot sits. And the hotspot, I shouldn't say right now, because the hotspot's always right there. But the plate moves, and it moves the older constructs out of the way of where, you know, this plume actually sits, because the plate's actually moving it out of the way. So just like with the Hawaiian hotspot, this is acting the same way. And that's true of all hotspots that have been around for a very long time. They're going to have a signature that is like a trail. This particular diagram also gets into other types of volcanoes too. Its focus is more than just what I'm showing you here, but I just wanted to give you an idea of the Yellowstone and its signature of volcanism over the many million years it's been in existence. All right, so that is the end of this lecture. Thank you very much, and I'll see you in the next one.